In today's video, we're going to be talking about power with an impedance. Specifically, we'll be exploring the concept of power for a pure load. What does that mean? Well, the first thing we need to do is draw out a circuit. And it's a AC and again voltage source. Its phasor is given as V angle 0 degrees. Sometimes we might also say Vm for V magnitude. And all it is attached to a single load that we call ZL, so it's a load impedance, not anymore is it just a resistance. And it could be a pure resistance, or it could be an inductor, or it could be a capacitor. However, it's just one of those things. That's what I mean when I say a pure load. What we'll be doing is looking at how the power through this load element differs when it's a resistor, an inductor, or a capacitor. In order to do that, we'll need to figure out I through the load as a phasor, and then notice that power is VI. Once we get voltage, which we know through the load is just Vm angle 0, and current, which we'll be using Ohm's law for, we can then get power. We'll need to use a little bit of trigonometry, but I'll show you as we go. Let's begin with a resistance. In a resistance, the impedance equals to whatever the resistor values is. The voltage, because it's in parallel, is Vm cosine of omega t. The current is going to be given as Im cosine of omega t, where if you'd like to know what Im is, it's Vm over R. And that's just using Ohm's law. The power then is Vm Im cosine squared omega t. And let's take a look at what that actually means. Whether Vm is positive or negative doesn't matter, so typically we take it as being positive. The reason it doesn't matter is because Im is just Vm over R. So when I multiply Vm by Im, I'm going to get a positive number no matter what happens. The cosine squared also is positive for all t. Therefore, power of time in a resistor is greater than or equal to 0 for all, that's the symbol for all, time. What this means is resistors always absorb. In other words, they're always heating up, always using energy. V and I are in phase for a resistor. There is no phase lead or lag between the current and the voltage in a resistor. That's not the case for another impedance. Let's look at an inductance. Here, the inductance is J omega L. The voltage is the same. But the current, because the current follows an integral relationship, is out of phase, or this is one of the rare times when I'd like to use a sine wave. So this is the current, and this is the voltage. Now let's take a look at what the power is. Power is VI, or Vm Im cos omega t sine omega t. This is where we have to dig into our calculus notes and take out a trigonometric identity. Cos theta, sine theta, for any theta, no matter what it is, in our case it's just omega t, is 1/2 sine of 2 theta. So let's plug this back in. The power in the inductor is Vm Im over 2 sine of 2 omega t. So, what does this mean, and how does it differ from that of a resistor? The first thing I'll do is plot the power. It's sinusoidal, and you'll notice that it's positive and negative. Remember, an inductor stores and delivers energy. During the positive phase, we have storage. During the negative phase, we have delivery. This means something quite remarkable. P average, the average power in a pure inductive load, is 0. We'll explain what's going on in just a second, but I'd like to show you that we actually have an almost identical arrangement for a capacitance as well. In a capacitance, the inductor is 1 over j omega c. We have the same thing with the voltage, as always. And because the capacitor has a derivative relationship, we actually get the sinusoid out in the first place, which we're going to stick with. So, power is VI, which is technically negative because of that. And again, I'm using the same trigonometric identity as I used for the inductor. Now, this isn't really relevant. And the reason is because it's a sine wave. So at the end of the day, when it starts to oscillate up and down, we don't really care whether it started positive or negative, because we're interested in how much power we need to supply. So, what's actually happening? Does it mean that I don't need to have a power source in my circuit in order for us to have a current or a voltage? No. There's this long distinction between the average power and the instantaneous power, and this is very crucial to understand. P average is 0. This means that the elements, both the inductor and the capacitor, absorb as much as they supply. That makes sense from the perspective of the conservation of energy. If I put in 10 joules in 1 second, and I don't get 10 joules out ever again, then I've violated conservation of energy. Similarly, if I put in 10 joules but I get out 100, I've violated conservation of energy. Since everything is oscillating up and down, positive and negative, I should be expecting to get stuff out and in. However, P instantaneous is not 0. This comes from our sources. What it means is that if my power is, say, 10 watts instantaneously, in other words, I must be able to supply 10 watts, then regardless of whether my capacitor is absorbing or supplying energy, my power supply must still be able to handle 10 watts. This energy is still moving around. It's just not being absorbed like it is in the resistors. This power is called reactive power. And reactive power is a term that we'll be talking about in the next video.